I want to point out on your exam, 2b is the same molecule as it will be for part 3, and the 4 points becomes 10, 15 when you're done. So you got to do a good job on 2b if you hope to do well on 3a and 3b. And yes, we'll get started right now. So the patterns we're supposed to know in functional group short forms are this pattern with a CHO going that way is an aldehyde. And there's only one proper way to draw aldehydes. We will be doing that shortly. And the other pattern we're supposed to recognize is CO2H is a carboxylic acid. And we have to be able to draw those the proper way as well. Don't invent your own way. And that's how I like to start. Look for those because look at all the old exams. Almost every time you're going to have an aldehyde or a carboxylic acid or a carboxylic ester, which is in a very similar family to the carboxylic acid. So an aldehyde, when it's going from left to right, has the carbonyl there, carbonyl, C double bonded to O with an H. And because this is a Lewis structure question, you can't stop there. You've got to show the lone pairs on the O. So that's the part on the far left, the aldehyde part, and the part on the far right. So there's the left, it'll connect to something. If my pen was on, it could. And on the far right, you have to draw a carbonyl again, double bond O, and this time the other O is part of a hydroxyl. So don't call it a functional group called a hydroxyl. Don't call it a functional group called a carbonyl. The carboxylic acid is the functional group, and it has both of those features. Now we just got to do the skeleton that connects from the left to the right. And we'll just change colors. We're going to, next up is a C with a single H. And don't worry about filling the octets till we finish going from left to right. The next C has no H's. The next C has no H's as well. So 2 C's in a row with no H's. What does the parenthesis mean? If the parenthesis is in the middle of a molecule, I'll tell you what it always means. It's attached, this atom here is attached to the previous atom before the parentheses. So we're going to attach an N that has a bond to H. The N also has a bond to a C that has 3 H's. The parentheses means it's sticking off of the green chain. And don't forget, this is a Lewis question. So nitrogen's nature to get a full octet is to have 3 bonds and a lone pair. I was looking at my previous videos and those pink, I won't be doing those light pink lone pairs anymore. They didn't show up very well. So there we go. And back to the green skeleton. We've got the blue aldehyde carbon, the green C with 1 H, the green C with no H's, the green C with the nitrogen. Well, what is it after the nitrogen? Well, it's the chain continues on the outside of the parentheses to a C with 2 H's. C with 2 H's. And what's after that is the CO2H, and my spatial planning is never good. You will learn that this semester. That's okay. That's just a big long bond. Yes.
So whatever like is on the right side of like the chain, right? For like the Lewis structure, that's always going to be attached to whatever's on the left, if that makes sense. So like for
this
example,
over here
like
on the right goes backwards to the C with 2 H's. Yeah. And
no, I meant like with the Lewis structure, like not the drawing thing, just like the name of the molecule. So see how there's like the HCC and then the nitrogen, like the nitrogen
HCC, then the nitrogen group thing. Yeah. That's in the chain.
Yeah.
The H is off this C. And we're not finished down here. I just want to remind you, you're not finished. There's octet violations everywhere. But yeah, the HCC is here. H attached to C, attached to C. That's that left part. And continuing, we have a C with a C with a C, and the C has an NH off of it. And that parenthesis is independent. It's not in the middle of the chain. It's sticking off of the chain. Parentheses told us that. I don't think I answered your question.
Okay.
Did I?
Yeah. And then so for the hydrogens, they're always going to be attached to like usually the carbon that's on its left.
The previous
right?
carbon on the left, exactly. Yes.
Okay.
I want to point out though, you can do this. You could write a molecule. Here's a separate molecule, just a little guy. If you start with a hydrogen, there's nothing wrong with this. But it does kind of go against what you just said, right? Well, there's nothing to the left of the H's here. So what's it attached? Well, it's got to be attached to the next one, right?
Yeah. Okay.
Yeah. That one kind of, it kind of explains itself, doesn't it?
Yeah, since it's basically like a CH3 just written backwards.
Yeah,
so it'd be
that's
faced
right.
towards the left.
Right. And it's perfectly fine to write the same molecule like this. They're both okay. They're both the same molecule. Going back here, please do not put lone pairs on carbon. It will, the results that you get back when I grade your test, you're not going to be happy with. You're going to get a -1 every time you put lone pairs on a carbon in a Lewis structure. So how do you get octets full for carbon? Well, the octet's full here. We got 4 bonds, done. The octet is not full here, 3 bonds. You're allowed to put a pi bond, right? Don't put it to the left. You'll have an octet violation on the blue carbon if you put the pi bond there. Let's put pi's in red. You must put the pi bond there. It's not very nicely drawn pi bond. Here it is, much better. And that fills the octet for this carbon. It has 2, 4, 6, 8 electrons around it. Next carbon does not have an octet. It is surrounded by 2, 4, 6 electrons. You can't put a second pi bond to the left because that will be an octet violation here. The only choice you have is to put the pi bond here. And I believe that finishes all of our octets and gives us full credit for part 2b. And that's 2b. And the length of this bond is just bothering me here. There's nothing wrong with it. I'm just, sometimes the analytical chemist gets to me and says, the bonds should be drawn roughly the same. There. Okay, didn't change anything just then. And I'm going to put all my work for parts 3 on that same molecule. Here I can read them. I'm supposed to indicate the bond type for each bond. There's a bond type. It says, here, I'll read it for you. It's a sigma bond, which means it's the strong one between 2 atoms. A bond is always between 2 atoms, right? The hybridization of one of the atoms is sp, and the atom it's attached to is sp2. That's how we read this. And the hybrid orbitals overlap. They make this sigma bond, and now the hybrid orbitals don't exist anymore. They now form a new orbital called a molecular orbital, and that's the name of the molecular orbital right there. All right, so don't go looking for that molecular orbital. Just say, I'm going to label all the bonds in my molecule. If you skip any, then you're going to lose points. We don't like losing points. So I'll put my labels in purple. I'm going to say this is A. You can label them whatever you want. Numbers, letters. I had one student do like hieroglyphs and emojis and stuff. That's fine. Made it a little tricky for me to grade, but whatever floats your boat. It's the only bond between these 2 atoms. So what do you call the only bond between 2 atoms? It has to be this letter. must start with sigma or pi. Remember that. We're doing every bond in this molecule. If there's only one bond, it's a sigma. If there's two bonds, one of them is a sigma and the other's pi. All right. So here's a trick question. What's the hybridization on the hydrogen atom? Trick question. Hydrogen can't hybridize. The only orbital hydrogen can ever use is the s orbital available to the two atoms in the first row of the periodic table, hydrogen and helium. And we will not see helium in this course. It already has its full octet. Carbon here. How do you do hybridization? What are the two things you count? As per our last video, we count two things. We count
lone pairs.
Yes, lone pairs and
Bonds.
What kind of bonds?
Sigma bonds.
Sigma only. That's right. So I'm going to count up. I'm going to use my fingers. I got 1 sigma, 2 sigma, 3 sigmas, and no lone pairs. I put 3 fingers in the air and I say sp2. Is this a strange video without my face for the first time? Because I'm not seeing my face on my other screen.
No, your face is showing.
My face is there?
Mm-hmm.
Oh, okay. Oh, you know what I did? No, anyway, my face is a mystery to me. It's okay. So we just said the carbon is sp2. Now, are there any other H's bond to sp2 atoms? And the answer is yes, there's one more. So you don't have to redraw that label, you don't have to redraw the name, just the label. That is an sp2 carbon, sigma 1, sigma 2, sigma 3, no lone pairs. That's a total of 3 things. Don't call this the same label. Don't call this the same label. And don't call any of these the same label. Those are going to be B. I like getting my H's out of the way. That's just my personal preference. You can do this in any order you want. It's a sigma bond again with the hydrogen providing the S. And in this instance, count the sigmas, 1, 2, 3, and the lone pair is 4. 4 fingers in the air, and that's sp3. There's a significance to that. This bond here will be weaker than this bond here because this portion of the bond is 33% S and this portion's 25% S. We didn't get into that. I'm not going to ask you to explain that on the test, but there's a reason why we do these things. And these are all sp3 bonded to S. Y is the carbon sp3, 4 sigmas, no lone pairs. Y is the oxygen sp3, 1 sigma, 2 sigma, that's 2, and 2 lone pairs, that's 2 more, that's 4 fingers in the air. And I didn't label this is B or this is B. And coming up with C, I don't know, I'm going to go left to right until I've done every bond. And I'm going to do my pi bonds last. Some of you know why I do pi bonds last. Anybody want to? It's not serious. It's kind of a joke. Why do we do pi bonds last?
For dessert.
You've seen the videos. Yes, you have pie for dessert. Okay, so C, hybridization of the carbon on the left is sp2. The one on the right is also sp2. So here you're going to have 2 hybrids overlapping to make this molecular orbital with that name. And I believe there's only one other C in this molecule. It's a sp2 here because 3 sigmas, no lone pairs, and sp2 for oxygen as well. 1 sigma and 2 lone pairs, 3 fingers in the air, sp2. And then we'll keep going. We have a D here. And if you look backwards, this is the same. Yeah, I think I have room for one more letter here, keeping everything on the screen. Sigma between sp2 on one of the atoms and sp on the other. This one is sp. 2 sigmas, no lone pairs. Now look at this other one. It's this bond here. It's sp2 here to sp here. sp2 to sp. Saying sigma sp2 to sp is identical to saying sigma sp to sp2. Does not matter the order that you list these two. And E, I don't think we're going to need any more sigmas after E. Sigma between sp2, oh, we do need one more. sp2 on the left and sp3 on the right. And then we have two F's. Those are sigmas between two atoms that are both sp3. And I didn't label it, but I already have a letter for it. Which letter is this one? Take a stab at it. Anybody? Don't be shy.
Wait, what was the question?
Which label that I already have on this down here goes right here for this sigma bond? And I'm going to use the same label here.
So that's the one on the left is a sp3.
Correct?
sp2.
Yes. I need the name that has sp3 and sp2 in it.
OE.
Yes.
So it doesn't matter which way they're going, like if
exactly.
It's going from
okay. sp2, sp3 is the same as sp3, sp2. And this is sp2 on the left, sp3 on the right. Doesn't matter left or right. So it is the time for dessert. We'll do pink dessert. We'll go G for pi. Now, pi bonds don't use hybrids. They use unhybridized p orbitals. And if you do this, you're going to get partial credit. Two p orbitals overlapping to make a pi bond. You have to tell me that you know the only way for p orbitals to overlap to make a pi is if they have the same orientation. So you know there's three types of p orbitals. Oh, I forgot. My finger also writes on the screen. Okay. They have to have the same orientation. So we can do px, px if you want, or py, py. And call that G. I am not going to call this one G, and I'll talk about that in a second, but I am going to call this one G. And because you use the py orbital to make a bond to the carbon to the left, you can't use an orbital again for another another bond. Just like when you learned in 141, when you filled an orbital, you had to move to the next one. It's the same story here. You've used your py, you got to use another p to go this way. So just give me a name where the p's match. Tell me you know it's a pi bond. We can go PZ, PZ. We're back to the main course, pizza, pizza. And then we have H. And
wait, so it doesn't matter if you put it as a PY or a PZ or like a PX?
Correct. As long as they match, then I am a happy teacher grading your exam.
Okay.
Okay. And the last part is the geometry of a central atom. Now, central atoms are quite easy to define. I'll tell you what aren't central atoms. These H's are not central. They're on the outside. And these two O's are not central because they're on the outside. They're only bonded to one other atom. But this O is a central atom. It's got more than one thing attached. And we're going to just do all of the labels. We'll do these in baby blue. Every carbon that is sp2 can be given the same label. And you've got to tell me two parts. You have to tell me the name of its geometry. And when you have three sigma bonds and no lone pairs, you say trigonal planar. I'll accept the short form trig planar. And I also need the angles for trigonal planar. You only get a half credit if you give me the names. 120 degrees. And then I'll go to an atom I haven't labeled yet. how about this one? I think it's unique in the structure. It's an sp carbon, so its angle's 180. And the name of the geometry is linear. And moving forward, you'll see my keys never have a label of a C, although I did C here. Kind of contradicting what I just said, but I don't know. For these, I skipped the letter C because it looks too much like a carbon atom. And D, you don't have to skip the letter C. You don't have to put up with my nonsense. There's another D here. Those are two carbons that are sp3. The angle for sp3 is always 109.5. And when there's no lone pairs, we call it tetrahedral. There's two other atoms that are 109.5 because they're sp3, but don't give them the same label. The angle, 109.5 for that, and 109.5 for my not yet labeled F, because they're sp3. Everything that has an angle of 109.5 is sp3. E is missing one of the corners of a tetrahedron. We call that a pyramid. Pyramidal. And F is missing two corners of a tetrahedron, and we just call that bent. And that is the end of our first segment.